Ttdp, also known as Train Topology Discovery Protocol, is designed to provide a flexible network environment for railway applications, which must constantly adapt to changing train configurations. The protocol will identify the location of onboard network devices and reassign an IP address to them based on the new arrangement of the carriages. This will help train operators vastly improve their operational efficiency. The following video clip will show how Ttdp works. Generally, networks are designed to work in a fixed environment and thus lack flexibility. Changing network topologies will require the entire network to be reconfigured. In railway applications where train carriages are constantly changed or rearranged, this is a pain in the neck because IT staff must spend a lot of time adjusting network configurations manually, leading to enormous management burdens and even worse, a high possibility of errors. Thanks to constant improvement in network technologies, a flexible network automation technology specific to railway applications has come into being, that is Ttdp. Oring has created a demo box simulated deployment in the train. The demo box includes a Ttdp-enabled Ethernet switch and an IP camera connected to it. The IP camera is powered by the switch through its PoE port. M2M connectors are used in the demo box to resemble connections in actual trains. Traditionally, onboard switches have a fixed IP address that follows them wherever they go. For ease of management, the IP address of the switches are based on the sequence of the train carriage. This would cause confusion to the operators when the train carriages are rearranged, because the IP addresses will not match the new order of the train carriages. Therefore, the operators must reconfigure the switches manually. With Ttdp, the problem can be solved. The auto-negotiation feature of Ttdp enables the system to perform network configuration tasks automatically, without the need for operator intervention. When carriages are changed or rearranged, the switch in the head carriage will negotiate with the switches in the other carriages and assign them an IP address based on the new arrangement of the trains. Hence, the system will always be able to reach a given device at a given train carriage. As you can see here, the IP addresses for the second and third train carriages will remain the same even though they have switched places. However, end devices connected to the switches such as IP cameras must also support Ttdp for auto-negotiation to work. Take IP surveillance for example. The multi-tile screen are configured to display surveillance images of each car by their sequences. So car 1 screen will always show the images of the first carriage. Car 2 will show the second carriage images and so on and so forth. Without Ttdp support, the images will be misplaced when the carriages are rearranged. Therefore, when camera B and C switch places, car 2 screen will continue to show images from camera B, even though it is now in the third carriage. Car 3 screen will show images from camera C, which is now in the second carriage. This is caused by fixed IP addresses of the IP cameras. With Ttdp support, the IP cameras will receive a new IP address based on the new arrangement of the train. Hence, each screen will display correct images. This is where Oring's DHCP binding technology steps in. It allows the switch to negotiate with the IP cameras and other end devices and reassign them a new IP address based on their locations. As you can see here, when switch B and C change places, both the IP addresses of the switch and the IP cameras will change accordingly. The IP addresses will always match the order of the train carriages and the screen will always display correct surveillance images. Ttdp and DHCP binding also works perfectly for adding and removing train carriages. When switch B is removed and switch D is added, switch C, which takes car B's place, will be assigned with the new IP address based on its location, which is the IP address of the switch B. The added carriage where switch D belongs to will also receive a new IP address, which is the original IP address of switch C, because switch D is now in the fourth carriage of the train. When switch B and C are replaced with the new switches E and F, they will inherit the IP address of B and C due to their arrangement in the train consist. Therefore, the screen originally shows the images from switch B and C, now display images from switch E and F. Through Ttdp, Oring switches will detect changes of the train and negotiate with the network devices to assign them a new IP that matches the new arrangement of train carriages. Ttdp optimize inter-consist communication efficiency, making network faster, more precise and more flexible. Ttdp not only saves network configuration time but also ensures safe train operations, as man-made errors are significantly reduced. While Ttdp has no problem working in daisy chain topology, some configurations must be made when it is running in a ring and bypass structures. Otherwise, errors may occur. In daisy chain topology with Ttdp enabled, the head train switch will assign a new IP address to the switch in adjacent carriages sequentially when train carriages are rearranged. However, in an O-ring topology, when the master link is down and the backup link is activated during operation, Ttdp will be implemented again. Therefore, the head train switch will assign a new IP address to every other switch sequentially, this time beginning from switch D as it is adjacent to switch A. As a result, the switches will be given a new IP address that doesn't match the arrangement of the carriages. Switch B's IP address now becomes 10.128.0.4, even though it is in the second carriage, and the IP address of the switch on the fourth carriage, which is switch D, is now 10.128.0.2. The same goes with the bypass structure. Normally, when an inline device breaks down, hardware bypass function will pass traffic to the next active switch, avoiding the broken device to ensure uninterrupted data transmission. In this situation, the head train switch will reassign an IP address to its adjacent switch due to Ttdp function. As a result, switch C will have a new IP address 10.128.0.2, even though its arrangement remains unchanged. To avoid this problem, the following settings must be done. In a ring topology, you must set the forward port of the ring master to card 2 and the blocking port to card 4. This will ensure Ttdp to work functionally in normal conditions. Next, you must turn off Ttdp setting on the web interface of the switch by setting inog_flag to inhibit. This must be done before the rearranged train starts running. These settings will ensure the IP address of each switch in a ring or bypass topology remains the same during operation. In this way, when the master link is down and the redundant link is enabled, the head train switch will not reassign an IP address for other onboard switches. All switches will continue to use the same IP address until Ttdp is enabled at next train arrangement. And the switches in a bypass structure will also continue to use the same IP addresses when an inline device fails.
大家好，今天我们要为大家介绍 Ttdp 这一个协议。那 Ttdp 呢，它其实是由一个这个国际标准组织，这个国际电工委员会 IEC 所颁发的这个协议。那它颁发的时候，它把它定义在这个 IEC 61375/2/5。哇，我们模拟了一个实际在这个火车现场会出现的这个火车调度现象。因为在火车在实际车厢分配的时候，常常有车厢调度的问题。如果在车厢调度之后，它很难照顺序再依序帮你排序，它可能是随机抽换了2台车厢，或者车厢顺序会有变更。那这时候用一般的 IP 分配机制，它的 IP 就会造成混乱，那可能就会失去了它管制的效果。但如果有 Ttdp 协议之后呢，我们可以看到第2张图，这个图面上我们把 B 跟 A 2个车厢做调换了，但是 Ttdp 开启之后呢，它的 IP 分配，第一节车厢依然是 10.128.0.1， 那第2节它虽然是 B 车厢，但它却得到了这个 10.128.0.2， 那第3节呢就是 10.128.0.3， 所以呢，即使我们调换了 B 跟 A 的顺序，但是 IP 的顺序依然是正确的，这样我们就可以得到一个正确的车辆排序的管制。